We've seen how to solve 2 by 2 systems. Now let's see how to generalize those ideas to m by n systems. So these are systems with m equations and n unknowns. Here's our first example. You could have the system x plus y minus z is equal to 1, x minus y plus 2z is equal to 0, and 2x plus z is equal to 2. So for this example, I think I'll generalize the substitution approach. So if I do the substitution approach, I'm going to take the bottom equation and solve for z. If I write this in terms of z, I get z is equal to 2 minus 2x. Then I could take that choice of z and plug it into the first two equations to get a 2 by 2 system, which I know how to solve. So I get x plus y minus 2 minus 2x is equal to 1, and x minus y plus 2z, well, z is equal to 2 minus 2x. That should equal 0. So rewriting this system, collecting the like terms, so collecting the x's, I think I will have 3x plus y is equal to 3, and negative 3x minus y is equal to negative 4. I have a 2 by 2 system. I could solve in any approach I like. This example is perfect for adding the two equations together, the elimination method. So I'm going to add the two equations. The 3x and the negative 3x cancel. The y and the negative y cancel. So this left side becomes 0. The right side becomes negative 1. I have 0 is equal to a non-zero number. That's false. That's not true. So that implies that there is no solution to this system. This is the analogous situation to having two parallel lines that never intersect. So the original system also no solution. That was an example of the substitution method, but I prefer for these problems the elimination method. So let's do an example using that approach. Maybe I can have x plus y plus z equals 0. Let's say x minus y is equal to 1, and y minus z is equal to 1 again. I'm going to perform various row operations on the rows of this system. And the first one I'm going to do is I'm going to take row 2 and I'm going to subtract away row 1. So I'm going to leave row 1 the same. I'm going to leave row 3 the same, and I'm only going to change the second row by adding, or actually subtracting, row 1 from it. The reason I'm going to subtract row 1 is because I'm trying to eliminate this x right here. And so if I take this row and subtract the first row, I get rid of the x. And I think I'm going to be left with negative 2y minus z is equal to 1 still. Oh, this should be a 1 as well. Next, I'll give you an example of another row operation that you could perform. You can actually switch the order of rows if you want to. And I feel like I want to now. So I'm going to switch the row 2 and row 3 positions. So I'm going to swap where they are and write x plus y plus z is equal to 0, y minus z is equal to 1, and negative 2y minus z is equal to 1. So one of the row operations I did was changing a row by adding a multiple of another row to it, and this row operation was just to switch their order. Now, switching the order of how I write the system clearly does not affect the solutions. Lastly, I will do another row operation. I'm going to take row 3 and change it. I'm trying to eliminate this y here. So to eliminate that y, I'm going to add 2 copies of row 2. I don't want to add a copy of row 1 because that would reintroduce an x. If I do this row operation, I'm going to leave row 1 the same. I'm going to leave row 2 the same. But I'm going to add 2 copies of row 2 to row 3. That eliminates the y variable. It's not there anymore. I believe I would get minus 3z is equal to 3. This is a good system to solve, better than what I started with, because the bottom row only contains one variable, z. So z is present alone in the bottom equation. Then y and z are present alone in the middle equation, and x is introduced only in the top row. This is what's known as a triangular form of a system, because the shape of the rows creates almost like a triangle, because each new variable is introduced reading from bottom to top. Here I can find my solutions. My solutions apparently tell me that z has to be -1. If z is -1, I could put that into the middle equation to find that y is equal to 0. And if I put y is equal to 0 and z equals -1 in the top equation, x has to be 1. So that's the only solution to this system. I'd like to clearly write down the 3 and only 3 legal row operations you can use when solving a system. So these are the 3 and only 3 row operations. The 3 row operations are, number 1, you can add a multiple of one row to another. That's a common row operation. I did it in the first step here, and this step here, I took row 3 and added a multiple of row 2. I took row 2 and added a multiple, that multiple was -1, of row 1. So that's a row operation that you're permitted to use. The second row operation is you can switch 2 rows. You could just switch where they're written, like I interchanged the positions of row 1 and row 2 here. And the last thing that you're allowed to do, I didn't do it in this top example, but you're additionally allowed to multiply a row by a non-zero number. So for example, if I wanted to, I could multiply this row in this last triangular system by -1/3. You may want to do that so that you have a leading coefficient of 1 in front of each row. That's optional. So let's finish this video with one more example of using the 3 row operations to solve a linear system. Why don't we go bigger? Why don't we solve a 4x4 linear system? So x plus y plus z plus w is equal to 0. 2y plus 4w is 6. Z minus w is equal to 0, and y plus z is equal to 1. So using these row operations, you can do various things. For example, I can use row operation 3 and take row 2, and notice that row 2 contains every number divisible by 2, so it's natural to do 1/2 row 2. So if I do 1/2 row 2, row 1 stays the same. I don't want to copy everything over and over again, so I'm just going to put a line there to mean that I have the same row as before. But this row becomes y plus 2w is equal to 3, and row 3 and row 4 are the same. Maybe now I will do row 4 minus row 2, because I want to eliminate this y here. I'd like to get a triangular system. So if I do row 4 minus row 2, the top row is the same. The second row is still this row, so I'm going to put a line there to denote that I haven't changed anything. The third row hasn't changed, but the fourth row I believe will become, so I'm going to take row 4, and I'm subtracting off this, so I'm going to get a z still. Z minus 2w is equal to, I think it'll be negative 2. Oh, I'm subtracting off this row, excuse me. And maybe one more move will make it triangular. So I'm going to do one more move, and I think I could do row 4 minus row 3. Now I'm going to write down the whole system in detail so we could see that I indeed have a triangular system. So my first row, the same. My second row is y plus 2w is 3. My third row is z minus w is equal to 0. And I think my last row just becomes negative w equals negative 2. So I have my triangle that I like. The last row contains only w. So w I know is 1. Oh, excuse me, 2. W is 2. Now I know w is 2. I could work my way up. Z has to be positive 2. Now y has to be, let's see here, w is 2, so that's 4. So y has to be negative 1. And then x plus y plus z is w, so x is negative 3. Okay, wonderful.